In this lesson, we'll examine even and odd numbers and some relationships that exist between them. To begin, every integer is either even or odd. So these are the even numbers, and these are the odd numbers. Some important facts to remember about even and odd numbers are as follows. First, even and odd numbers include negative values, so for example, -17 is considered an odd number. Next, 0 is an even number, and you will see some questions that test this fact. Also, even numbers are divisible by 2, which means that all even numbers can be expressed as 2k, where k is an integer. Another way to say this is that the prime factorization of an even number will include at least one 2. Conversely, odd numbers are not divisible by 2, which means the prime factorization of an odd number will not include any 2's. And finally, odd numbers can be expressed as 2k plus 1, where k is an integer. Now, most questions related to odd and even numbers will test your knowledge of a handful of rules. So let's take a look at these rules. The first set of rules involve the outcomes when integers are added or subtracted. For example, if you add or subtract two odd numbers, the result will always be even. Here are some examples of this. The next rule says that if you add or subtract an odd number and an even number, the result will always be odd. These examples illustrate this rule. The last rule says that if you add or subtract two even numbers, the result will always be even, and you can see this in the following examples. Now, these rules can be summarized as follows. If the two numbers are the same, that is, they are both odd or both even, then the sum or difference will always be even. If the two numbers are different, that is, one is odd and the other is even, then the sum or difference will always be odd. The next set of rules involve multiplication. First, the product of two odd numbers will always be odd, and this can be seen in these examples. Next, the product of an odd number and an even number will always be even, as is shown here. And finally, the product of two even numbers will always be even, as you can see in these examples. These rules can be summarized as follows. First, the product of any number of odd integers will always be odd. So if several odd numbers are multiplied together, the product will be odd. Second, once an even number enters the picture, the product will always be even. So if we multiply several numbers and one or more of them is even, then the product will always be even. Let's take a closer look at these two rules. Now we're going to use some prime factorization to show why these rules work. The first rule says that the product of any number of odd integers will always be odd. For example, let's find the product of 4 odd integers. According to the rule, the product should be odd. Let's see why. To begin, we'll take this first odd number and find its prime factorization. Since the number is odd, we know that the prime factorization will not include any 2's. The next number is also odd, so its prime factorization will not include any 2's either. The same applies to this number and this number. From this, we know that the entire product here does not include any 2's. As such, the product must be odd. Now let's examine the second rule. It says that once an even number enters the picture, the product will always be even. So, according to the rule, the product in this example should be even. Let's see why. To begin, we'll take all of the odd numbers and find their prime factorizations. Since these numbers are all odd, we know that their prime factorizations will not include any 2's. Now we'll take the even number and find its prime factorization. Since this number is even, we know that its prime factorization must include at least one 2. So now, when we examine the entire product, we can see that it includes at least one 2. This means the product is divisible by 2, which means the product must be even. Okay, now let's examine what happens when we divide integers. you will find that the rules for division are not nearly as concise as they are for addition, subtraction, and multiplication. Let's begin by developing a rule for what happens when we divide an even number by another even number. So we'll try a few numbers and see what happens. For example, when we divide 4 by 8, we get 0.5, which is not an integer. However, when we divide 12 by 6, we get 2, which is an integer, and an even integer at that. And when we divide 20 by 4, we get 5, which is an odd integer. So it appears that when an even number is divided by an even number, the result can be a non-integer, or an even number, or an odd number. Okay, now let's see what happens when we divide an odd number by an even number. When we try this, we see that the quotient can never be an integer. So we can conclude that an odd number divided by an even number can never be an integer. Okay, what about an even number divided by an odd number? Well, sometimes when we divide an even number by an odd number, we get an outcome that is not an integer. Other times we get an even integer. So we can say that if an even number divided by an odd number yields an integer, then that integer will be even. Finally, what happens when we divide an odd number by an odd number? Well, sometimes we get an outcome that is not an integer. Other times the outcome is an odd integer. So we can say that if an odd number divided by an odd number yields an integer, then that integer will be odd. Okay, now let's take some of our rules and apply them. Let's begin by determining whether the following evaluates to be an odd number or an even number. Now, when it comes to adding and subtracting even and odd numbers, we must do so in pairs. So for this question, we'll begin with this. Here we have an odd number plus an even number, so the sum will be odd. Now we'll examine this part. An odd number minus an odd number is even, which leaves us with an even number minus an odd number, which is odd. So our expression evaluates to be an odd number. Now let's examine a multiplication question. Is this product even or odd? Well, for products, we don't need to examine the pieces in pairs as we did for addition and subtraction. For products, all we need to do is look for even numbers. Since we have an even number here, we know that the product will be even because once an even number enters the picture, the product will always be even. Let's try one more product. In this question, we can see that there are no even numbers, so the product must be odd. Now, some questions involving odd and even numbers will require you to determine whether certain expressions evaluate to be either odd or even. Other questions will require you to draw conclusions based on certain information. For example, if a and b are both integers and their sum is odd, what conclusions can we draw about a and b? Well, if the sum is odd, we know that one number must be odd and the other number must be even. Okay, what if a minus b yields an even number? What can we say about a and b then? Well, here we can conclude that either both numbers are odd or both numbers are even. What if the product of these 6 integers is even? What can we conclude with absolute certainty? Well, if the product is even, then at least one of these 6 numbers must be even. Finally, if we are told that the product of 6 numbers is odd, then we know for certain that all 6 numbers must be odd. Okay, so these are some of the rules you need to know when tackling questions involving odd and even numbers. Be sure to know them. In this lesson, we'll examine a systematic technique for drawing conclusions about expressions involving even and odd numbers. To demonstrate this technique, let's see what conclusions we can draw about x and y if we're told that xy plus y is odd. Well, to begin, this expression involves 2 variables, x and y, and each variable can be either odd or even. So there are several different cases to consider. X and y can both be odd, or x can be even and y can be odd, and so on. Now, each of these cases will cause our expression xy plus y to be either odd or even. To keep track of the different cases, we'll use a table, and for each case we'll determine whether the expression evaluates to be odd or even. So what are the possible cases here? Well, x and y can both be even. X can be even and y can be odd. X can be odd and y can be even. Or both variables can be odd. So there are 4 different cases to consider. Now let's see what effect each case has on our expression xy plus y. So for the first case, we'll replace the x's and the y's with e to show that they are both even. To evaluate this, we'll apply our rules regarding even and odd numbers. So in this first case, we have an even number times an even number, which is even, and then to this we add an even number, which will result in an even number. So for the first case, where x and y are both even, the expression xy plus y evaluates to be even. For the next case, we'll plug in e's and o's for the even and odd numbers. When we apply our rules here, we see that the expression evaluates to be an odd number. We'll follow the same steps for the other 2 cases as well. So we now know the outcome for each of the 4 cases. Now we're told that the expression evaluates to be an odd number. When we examine our table, we see that there is only one case where the expression evaluates to be an odd number. In this particular case, x is even and y is odd. So we can conclude with certainty that x must be even and y must be odd. Now some students may find it cumbersome to plug e's and o's into the expression and then apply these rules for each case. So another strategy is to plug actual numbers into the expression. For example, if x and y are both even, we can replace both variables with 2's. When we do this, our expression evaluates to be 6, which is even. Now it doesn't matter which odd numbers and which even numbers you plug in. However, it's a good idea to use small numbers to make your calculations easier. So for odd numbers, plugging in a 1 will make calculations easy, and for even numbers, 2 is a good number to use. Now using a 0 for even numbers can make calculations even easier. However, the only drawback is that a 0 might get confused with an O, which represents odd numbers. The important point here is to use small values when plugging in numbers. Okay, for the next case, we'll plug a 2 in for the even number and a 1 for the odd number. When we do this, our expression evaluates to be 3, which is odd. We can continue this method for the other 2 cases, and when we do so, we see that our results in this table are the same as they were in the first table. Only one case results in our expression evaluating to be an odd number, so we can be certain that x is even and y is odd. Okay, let's try another one. Let's say that we're told that 6x minus 3y evaluates to be an odd number. If this is true, what conclusions can we draw about x and y? Well, we'll use the same strategy to examine the 4 possible cases. So for the first case, we'll plug in e's to represent even numbers, and then by applying our rules, we can see that the expression evaluates to be an even number. Following the same steps, we can test the other 3 cases as well. Alternatively, we can plug even and odd numbers into our expression and then evaluate them to get identical results. We've now tested all possible cases. Now we're told that the expression evaluates to be an odd number. When we examine either of our tables, we see that there are 2 cases in which the expression evaluates to be an odd number. So there are 2 possible conclusions we can draw. Either x is even and y is odd, or x and y are both odd. Either of these 2 cases can be true. Okay, as you can see, we now have a systematic technique for drawing conclusions about expressions involving even and odd numbers. So when you encounter a question involving even and odd numbers, consider creating a table to test the various cases. If you use a table, you can use e's and o's to represent even and odd numbers, and then apply the following rules. Or you can plug even and odd numbers into the expression, and then evaluate the expression. Finally, once you've tested each case, you can draw conclusions based on the various outcomes.